Choice of programming languages. In this video, we are going to see about choice of programming languages. A programming language is a tool, and even a good tool cannot be the right tool for all jobs. Over the years, the pros and cons of object-oriented programming languages have been debated, are now seen in Usenet news groups, conferences, articles, books, and other forums. Testing is important for application system written in any language. Just as testing object-oriented software differs significantly from testing conventional software, important but more narrowly focused differences arise when testing systems written in various object-oriented languages. Any discussion of object-oriented testing would be incomplete without consideration of these programming language differences. The general solution followed by idioms, that is, language-specific considerations. 6 object-oriented programming languages are considered here: ADE 95, C++, EFL, Java, Objective-C, Smalltalk. All have been used on large and critical applications, and all are widely available. These languages are not exotic research tools or proprietary systems with arbitrary constraints intended to extract tribute. The code examples are a beginning, not an end. Many of them use code fragments to illustrate a particular concept. A comment delimiter followed by an ellipse indicates that a typical implementation would be provided at this point. Term, definition, synonym. Abstract class. A superclass that provides common features but is not intended for direct instantiation. Deferred type, that is ADE 95, abstract base class, that is C++, deferred class, EFL. Accessor, a method that does not change the state of an object. Function, ADE 95 EFL, const function, C++, get method. Argument, a formal parameter of a message. Class variable, an instant variable that belongs to a class. Static data member, C++. Class, a representation or implementation of a source code unit from which objects may be created. Type, ADE 95. Class interface, the features of a class, methods, and instant variables that are visible to other classes. Argument list, C++, Smalltalk, signature, EFL. Client, a class that is object that sends a message to another class that is object, possibly itself. Cluster, a group of classes that supports some common purpose but that may not have explicit group interfaces. Group of types in a package, ADE 95. Feature, a method or an instance variable. Inheritance, inclusion of superclass features in a subclass. Instance variable, an object or primitive data type that is defined in a class. Object, ADE 95, data member, C++, entity, EFL, attributes. Instantiation, the creation of an object from a class. Declaration, ADE 95, construction, C++, creation, EFL. Message, a static or dynamic activation of a method. Call, ADE 95, C++, EFL. Method: a source code unit defined within the scope of a class that is translated into a callable executable. Member function, C++, routine, EFL, operation. Modifier: a method that can change the state of an object. Procedure, ADA95, EFL, set method. Object: a source code unit created from a class with a unique identifier, occupies memory, and is executable. Parameterized class: a class that can take a type parameter. Generic type, ADA95, template class, that is C++, generic class, EFL. Self: a variable that provides the object identifier of the object in which it is used. This, C++ and Java, current, EFL. Server: a class that is object that responds to a message sent by a client. Subclass: a class that obtains features by inheritance. Derived type, ADA95, derived class, C++, higher class, EFL, descendant class. Superclass: a class from which other classes inherit. Base type, ADA95, base class, C++, ancestor class, EFL, parent class. Coding standards. In this video, we are going to see about coding standards. Programmers spend far more time reading code than writing code. Over the life of the code, the author spends a considerable time reading it during debugging and enhancement. Coding standards provide rules and guidelines for some aspects of programming in order to make code easier to read. Most organizations that develop software regularly develop their own standards.
A comprehensive coding standard encompasses all aspects of code construction. While developers should prudently implement a standard, it should be adhered to whenever practical.
Completed source code should reflect a harmonized style, as if a single developer wrote the code in one session. At the inception of a software project, establish a coding standard to ensure that all developers on the project are working in concert. When a software project incorporates existing source code or when performing maintenance on an existing software system, the coding standard should state how to deal with the existing code base. The readability of the source code has a direct impact on how well a developer comprehends a software system. Code maintainability refers to how easily that software system can be changed to add new features, modify existing features, fix bugs, or improve performance. Although readability and maintainability are the result of many factors, one particular facet of software development upon which all developers have an influence is coding technique. If one consistently applies a well-defined coding standard, apply proper coding techniques, and subsequently hold routine code reviews, a software project is more likely to yield a software system that is easy to comprehend and maintain. Although the primary purpose for conducting code reviews throughout the software development lifecycle is to identify defects in the code, the reviews can also enforce coding standards in a uniform manner. Adherence to a coding standard is only feasible when followed throughout the software project from inception to completion. The software coding standard shall restrict the use of language features which are not statistically determinable or where the implementation is compiler dependent. Keep software units small while minimizing data flow between units. Discourage the use of global variables and data. Encourage reuse as far as this assists comprehensibility, maintainability, and integrity. Enhance readability by the appropriate use of upper and lowercase letters, meaningful identifiers, comments, black lines, and indentation. Maximize use of the strong typing facilities provided by the language. Avoid use of complex or obscure language features which programmers may have difficulty in using. Enforce the use of simplified language syntax, using as far as practical one syntactical nature at the time. The software coding standards shall contain procedures and guidance on how to avoid or detect known faults in the compilation system and target hardware. In general, coding standards provide guidelines for programmers regarding naming conventions, file organization, statements, layout, and comments. Testing process. In this video, we are going to see about testing process. The basic goal of the software development process is to produce software that has no errors or very few errors. In an effort to detect errors soon after they are introduced, each phase ends with a verification activity such as a review. However, most of these verification activities in the early phases of software development are based on human evaluation and cannot detect all the errors. This unreliability of the quality assurance activities in the early part of the development cycle places a very high responsibility on testing. In other words, as testing is the last activity before the final software is delivered, it has the enormous responsibility of detecting any type of error that may be in the software. Furthermore, we know that software typically undergoes changes even after it has been delivered. And to validate that a change has not affected some old functionality of the system, regression testing is done. In regression testing, old test cases are executed with the expectation that the same old results will be produced. Need for regression testing places additional requirements on the testing phase. It must provide the old test cases and their outputs. These limitations require that additional care can be taken while performing testing. As testing is the costliest activity in software development, it is important that it can be done efficiently. All these factors mean that testing should not be done on the fly, as is sometimes done. It has to be carefully planned and the plan has to be properly executed. The testing process focuses on how testing should proceed for a particular project. Functional testing or black box testing. In this video, we are going to see about functional testing or black box testing. Functional testing is also called as black box testing or behavioral testing. Black box testing methods focus on the functional requirements of the software. Test sets are derived that fully exercise all functional requirements. In black box testing, test cases are designed from an examination of the input or output values only, and no knowledge of design or code is required. The following are the two main approaches available to design black box test cases: equivalence partitioning, boundary value analysis (BVA). Advantages: more effective on larger units of code than glass box testing. Tester needs no knowledge of implementation, including specific programming languages. Tester and programmer are independent of each other. Tests are done from a user's point of view. Will help to expose any ambiguities or inconsistencies in the specifications. Test cases can be designed as soon as the specifications are complete. Disadvantages: only a small number of possible inputs can actually be tested. To test every possible input stream would take nearly forever. Without clear and concise specifications, test cases are hard to design. There may be unnecessary repetition of test inputs if the tester is not informed of test cases the programmer has already tried. May leave many program paths untested. Cannot be directed towards specific segments of code which may be very complex and therefore more error prone. Most testing related research has been directed towards glass box testing. Equivalence class partitioning. In this video, we are going to see about equivalence class partitioning. Equivalence partitioning. It is a black box technique that divides the input domain into classes of data. From this data, test cases can be derived. An ideal test case uncovers a class of errors that might require many arbitrary test cases to be executed before a general error is observed. In equivalence partitioning, the equivalence classes are evaluated for given input condition. Equivalence class represents a set of valid or invalid states for input conditions. Equivalence class guidelines can be as given below. If input condition specifies a range, one valid and two invalid equivalence classes are defined. If an input condition requires a specific value, one valid and two invalid equivalence classes are defined. If an input condition specifies a member of a set, one valid and one invalid equivalence class is defined. If an input condition is Boolean, one valid and one invalid equivalence class is defined. For example, area code. Input condition Boolean. The area code may or may not be present. Input condition range. Value defined between 200 and 700. Password. Input condition Boolean. A password may or may not be present. Input condition value. 7-character strings. Command. Input condition set containing commands noted before. Boundary value analysis BVA. In this video, we are going to see about boundary value analysis. Boundary value analysis BVA. A boundary value analysis is a testing technique in which the elements at the edge of the domain are selected and tested. Using boundary value analysis, instead of focusing on input conditions only, the test cases from output domain are also derived. Boundary value analysis is a test case design technique that complements equivalence partitioning technique. Guidelines for boundary value analysis techniques are: if the input condition specified the range bounded by values x and y, then test cases should be designed with values x and y. Also, test cases should be with the values above and below x and y. If input condition specifies the number of values, then the test cases should be designed with the minimum and maximum values, as well as with the values that are just above and below maximum and minimum should be tested. If the internal program data structures specify such boundaries, then the test cases must be designed such that the values at the boundaries of data structure can be tested. For example, integer d with input condition -2, 10. Test values -2, 10, 11, -1, 0. If input condition specifies the number values, test case should be developed to exercise the minimum and maximum numbers. Values just above and below this min and max should be tested. Enumerate data E with input condition 2, 7, 100, 102. Test values 2, 102, -1, 200, 7. White box testing. In this video, we are going to see about white box testing. White box testing. The structural testing is sometimes called as white box testing. The white box testing is a testing method which is based on close examination of procedural details. Hence, it is also called as glass box testing. In white box testing, the test cases are derived for examining all the independent paths within a module, exercising all the logical paths with their true and false sides, executing all the loops within their boundaries and within operational bounds, exercising internal data structures to ensure their validity, Cyclomatic complexity. Cyclomatic complexity is a software metric that gives the quantitative measure of logical complexity of the program. The cyclomatic complexity defines the number of independent paths in the basis set of program that provides the upper bound for the number of tests that must be conducted to ensure that all the statements have been executed at least once. There are three methods of computing cyclomatic complexities. Method 1. The total number of regions in the flow graph is a cyclomatic complexity. Method 2. The cyclomatic complexity, that is V of G for a flow graph G, can be defined as V of G is equal to E minus n plus 2, where E is total number of edges in the flow graph, n is the total number of nodes in the flow graph. Method 3. The cyclomatic complexity, that is V of G for a flow graph G, can be defined as V of G is equal to P plus 1, where P is the total number of predicate nodes contained in the flow graph. Let us understand computation of cyclomatic complexity with the help of an example. Consider the following code fragment with line numbered. To compute cyclomatic complexity, we will follow these steps. Step 1. Design flow graph for given code fragment. Step 2. Compute regions, predicate, that is decision nodes, edges and total nodes in the flow graph. There are three regions denoted by R1, R2 and R3. Nodes 1 and 3 are predicate nodes because which branch to be followed is decided at these points. Total edges is equal to 7. Total nodes is equal to 6. Step 3. Apply formula in order to compute cyclomatic complexity. Cyclomatic complexity is equal to total number of regions is equal to 3. Cyclomatic complexity is equal to E minus n plus 2. Cyclomatic complexity is equal to 7 minus 6 plus 2, which is equal to 3. Cyclomatic complexity is equal to P plus 1 is equal to 2 plus 1, where P is predicate nodes. There is node 1 and node 3 are predicate because from these nodes only the decision of which path is to be followed is taken, which is equal to 3. Thus, cyclomatic complexity is 3 for given code. Structural testing or white box testing. In this video, we are going to see about structural testing or white box testing. The structural testing is sometimes called as white box testing. In structural testing, derivation of test cases is according to program structure. Hence, knowledge of the program is used to identify additional test cases. Objective of structural testing is to exercise all program statements. Here, we will discuss 3 different approaches to structural testing: condition testing, loop testing, path testing. Condition testing. To test the logical conditions in the program module, the condition testing is used. This condition can be a Boolean condition or a relational expression. The condition is incorrect in following situations: Boolean operator is incorrect, missing, or extra. Boolean variable is incorrect. Boolean parenthesis may be missing, incorrect, or extra. Error in relational operator. Error in arithmetic expression. The condition testing focuses on each testing condition in the program. The branch testing in a condition testing strategy in which for a compound condition each and every true or false branch are tested. The domain testing is a testing strategy in which relational expression can be tested using 3 or 4 tests. Loop testing. Loop testing is a white box testing technique which is used to test the loop constructs. Basically, there are 4 types of loops: simple loops, nested loops, concatenated loops, unstructured loops. Simple loops. The tests can be performed for n number of classes where n is equal to 0, that means skip the loop completely. N is equal to 1, that means 1 pass through the loop is tested. N equal to 2, that means 2 passes through the loop is tested. N equal to m, that means testing is done when there are m passes where m is less than n. Perform the testing when number of passes is n minus 1 and n plus 1. Nested loops. The nested loop can be tested as follows. Testing begins from the innermost loop first. At the same time, set all the other loops to minimum values. The simple loop test for innermost loop is done. Conduct the loop testing for the next loop by keeping the outer loops at minimum values and other nested loops at some specified value. This testing process is continued until all the loops have been tested. Concatenated loops. The concatenated loops can be tested in the same manner as simple loop test. Unstructured loops. The testing cannot be effectively conducted for unstructured loops. Hence, these types of loops need to be redesigned. path testing. Path testing is a structural testing strategy. This method is intended to exercise every independent execution path of a program at least once. Following are the steps that are carried out while performing path testing. Step 1. Design the flow graph for the program or a component. Step 2. Calculate the cyclomatic complexity. Step 3. Select a basis set of path. Step 4. Generate test cases for these paths. Unit testing. In this video, we are going to see about unit testing. In unit testing, the individual components are tested independently to ensure their quality. The focus is to uncover the errors in design and implementation. The various tests that are conducted during the unit test are described as below. Module interfaces are tested for proper information flow in and out of the program. Local data are examined to ensure that integrity is maintained. Boundary conditions are tested to ensure that the module operates properly at boundaries established to limit or restrict processing. All the basis, that is independent paths, are tested for ensuring that all statements in the module have been executed only once. All error handling paths should be tested. Drivers and stub software need to be developed to test incomplete software. The driver is a program that accepts the test data and prints the relevant results, and the stub is a subprogram that uses the module interfaces and performs a minimal data manipulation if required. This is illustrated by following figure. The unit testing is simplified when a component with high cohesion, that is with one function, is designed. In such a design, the numbers of test cases are less and one can easily predict or uncover errors. Integration testing. In this video, we are going to see about integration testing. A group of dependent components are tested together to ensure their quality of their integration unit. The objective is to take unit-tested components and build a program structure that has been dictated by software design. The focus of integration testing is to uncover errors in design and construction of software architecture, integrated functions or operations at subsystem level, interfaces and interactions between them, resource integration and or environment integration. The integration testing can be carried out using two approaches: the non-incremental integration, incremental integration. The non-incremental integration is given by the Big Bang approach. All components are combined in advance. The entire program is tested as a whole, and chaos usually results. A set of errors is tested as a whole. Correction is difficult because isolation of causes is complicated by the size of the entire program. Once these errors are corrected, new ones appear. This process continues infinitely. Advantages of Big Bang. This approach is simple. Disadvantages of Big Bang. It is hard to debug. It is not easy to isolate errors while testing. In this approach, it is not easy to validate test results. After performing testing, it is impossible to form an integrated system. An incremental construction strategy includes top-down integration testing, bottom-up integration testing, regression testing, smoke testing. Top-down integration testing. Top-down integration testing is an incremental approach in which modules are integrated by moving down through the control structure. Modules subordinate to the main control module or incorporated into the system in either a depth-first or breadth-first manner. Integration process can be performed using following steps. The main control module is used as a test driver, and the stubs are substituted for all modules directly subordinate to the main control module. Subordinate stubs are replaced one at a time with actual modules using either depth-first or breadth-first method. Tests are conducted as each module is integrated. On completion of each set of tests, another stub is replaced with a real module. Regression testing is conducted to prevent the introduction of new errors. For example, in top-down integration, if the depth-first approach is adopted, then we will start integration from module M1, then we will integrate M2, then M3, M4, M5, M6, and then M7. If breadth-first approach is adopted, then we will integrate module M1 first, then M2, M6. Then we will integrate module M3, M4, M5, and finally M7. Bottom-up integration testing. In bottom-up integration testing, the modules at the lowest levels are integrated at first, then integration is done by moving upward through the control structure. The bottom-up integration process can be carried out using following steps. Low-level modules are combined into clusters that perform a specific software subfunction. A driver program is written to coordinate test case input and output. The whole cluster is tested. Drivers are removed and clusters are combined, moving upward in the program structure. For example, first components are collected together to form cluster 1 and cluster 2. Then each cluster is tested using a driver program. The clusters subordinate their driver module. After testing, the driver is removed and clusters are directly interfaced to the modules. Regression testing. Regression testing is used to check for defects propagated to other modules by changes made to existing program. Thus, regression testing is used to reduce the side effects of the changes. There are 3 different classes of test cases involved in regression testing. Representative sample of existing test cases is used to exercise all software functions. Additional test cases focusing software functions likely to be affected by the change. Test cases that focus on the changed software components. After product had been deployed, regression testing would be necessary because after a change has been made to the product, an error that can be discovered and it should be corrected. Similarly, for deployed product, addition of new feature may be requested and implemented. For that reason, regression testing is essential. Smoke testing. The smoke testing is a kind of integration testing technique used for time-critical projects wherein the project needs to be assessed on frequent basis. Following activities need to be carried out in smoke testing. Software components already translated into code or integrated into a build. The build can be data files, libraries, reusable modules, or program components. A series of tests are designed to expose errors from build so that the build performs its functioning correctly. The build is integrated with the other builds and the entire product is smoke tested daily. Smoke testing benefits. Integration risk is minimized. The quality of the end product is improved. Error diagnosis and correction are simplified. Assessment of progress is easy. System testing. In this video, we are going to see about system testing. The system test is a series of tests conducted to fully the computer-based system. The main focus of such testing is to test system functions and performance, system reliability and recoverability, that is recovery test, system installation, that is installation test, system behavior in the special conditions, that is stress test, system user operations, that is acceptance test or alpha test, hardware and software integration and collaboration, integration of external software and the system. Various types of system tests are recovery testing, security testing, stress testing, performance testing. Recovery testing. Recovery testing is intended to check the system's ability to recover from failures. In this type of testing, the software is forced to fail and then it is verified whether the system recovers properly or not. For automated recovery, then reinitialization, checkpoint mechanisms, data recovery and restart are verified. Security testing. Security testing verifies that system protection mechanisms prevent improper penetration or data alteration. It also verifies that protection mechanisms built into the system prevent intrusion such as unauthorized internal or external access or willful damage. System design goal is to make the penetration attempt more costly than the value of the information that will be obtained. Stress testing determines breakpoint of a system to establish maximum service level. In stress testing, the system is executed in a manner that demands resources in abnormal quantity, frequency, or volume. A variation of stress testing is a technique called sensitivity testing. The sensitivity testing is a testing in which it is tried to uncover data from a large class of valid data that may cause instability or improper processing. Performance testing. Performance testing evaluates the runtime performance of the software, especially real-time software. In performance testing, resource utilization such as CPU load, throughput, response time, memory usage can be measured. For big systems, for example banking systems involving many users connecting to servers, for example using internet, performance testing is very difficult. Beta testing is useful for performance testing. Testing tools. In this video, we are going to see about testing tools. Testing tools. A test tool is a software application that supports testing. Software testing tools are of immense use to develop quality software. Manual testing is time-consuming, error-prone, and requires a lot of infrastructure and manpower. All these drawbacks can be overcome if the testing process is automated. The testing tools reduce manual testing to a large extent, and the testing can be done automatically. Using these tools has many advantages. Once the software is ready for testing, the functionality of the software can be tested repeatedly to improve the quality and reliability. When the software has to be tested in different environments, that is different hardware platforms, different operating systems, using different browsers, etc., the labor involved can be reduced. Performance testing can be done without the need for many computers and many test engineers. The test tools simulate multiple users on a single machine. As compared to manual testing, finding out transaction response times when multiple users access the same application will be very easy. Testing process can be planned and managed effectively using these tools. Test reports can be generated automatically for later analysis and correction action. Testing can be done using tools that are available to test not only generic applications such as database application and websites, but also for DLLs, Visual Basic Programs, CABL software, Power Builder software, databases, standalone Java application, etc. The testing process can be managed efficiently, the planning can be done systematically, the tests can be scheduled efficiently, and the bug tracking can be done effectively. Hence, using automated test tools results in improvement in the quality and reliability of the software, drastic reduction in time, effort, and money spent on testing, a systematic approach to the testing process, efficient management of the testing process even if the teams are at different geographical locations. Taxonomy of testing tools. In this video, we are going to see about taxonomy of testing tools. A wide variety of software testing tools are available to cater to the different types of software, different programming languages, and to carry out different types of testing. These testing tools can be broadly divided into the following categories: functional or regression testing tools, source code testing tools, performance testing tools, Java testing tools, embedded software testing tools, network protocol testing tools, configuration management or bug tracking tools, testing management tools. Functional or regression testing tools. These tools are used to test the application software and web applications such as websites. As majority of the application involve graphical user interface GUI, the tools test the GUI objects and functionality automatically. These tools carry out black box testing. Source code testing tools. These tools check the source code of the application software. The testing is white box testing, and hence the implementation details are taken into consideration. A number of tools are available for checking line coverage, branch coverage, and path coverage. Tools are also available to test whether the source code is compliant to the standard coding guidelines and to generate metrics such as number of non-commented lines, number of commented lines, number of functions, etc. Performance testing tools. These tools are used to carry out performance testing or stress testing. These tools are very useful to test how the application works when multiple users access the application simultaneously. The application can be, for example, a database or a website. These tools simulate multiple users on a single machine, and hence you do not need many machines and many test engineers to do the performance testing. Java testing tools. As Java has become a popular programming language in recent years, a number of tools are available exclusively for testing Java application. These tools are for testing applications written in Java programming language and for testing Java classes. Embedded software testing tools. Testing embedded software is a very challenging task as the timing requirements for these applications are very stringent. In embedded systems, the code has to be optimized so that it occupies the minimum memory. IBM Rational Test Real-Time is a widely used test tool in this category. Network protocol testing tools. A number of tools available for testing networking and communication protocols. This software generates packets in correct and incorrect formats to test the networking software. NetIQ's Chariot is a network performance testing tool. Configuration management or bug tracking tools. In large software development projects, configuration management is a very important process. Also, when the test engineers report bugs, the managers have to track these bugs and ensure that all the bugs are removed. To facilitate this activity, good workflow management software is important. Many such tools which are web-based are available. Software testing management tools. These tools help in managing process-oriented software testing. Using these tools, the QA manager can create a formal test plan, allocate resources, schedule unattended testing, track the status of various bugs or activities, etc. Testing workbenches. In this video, we are going to see about testing workbenches. Testing is an expensive and laborious phase of the software process. As a result, testing and debugging tools were among the first software tools to be developed. These tools now offer a range of facilities, and their use may significantly reduce the cost of the testing and debugging process. Testing tends to be application and organization specific. Consequently, there is not a large market for closed testing workbenches. Rather, companies prefer to create their own testing workbenches using a combination of bought-in and locally implemented testing tools. Testing workbenches therefore invariably open systems which evolve to suit the needs of the system being tested. The below figure shows some tools which may be included in a testing workbench and the interactions between these tools. The tools which might be included in a testing workbench are Test Manager, Test Data Generator, Oracle, File Comparator, Report Generator, Dynamic Analyzer, Simulator, Test Manager. Manages the running and reporting of program tests. This involves keeping track of test data, expected results, program facilities tested, and so on. Test data generator. Generates test data for the program to be tested. This may be accomplished by selecting data from a database or by using patterns to generate random data of the correct form. Oracle. Generates predictions of expected test results. Oracle may either be previous program versions or prototype systems. Back-to-back testing involves running the Oracle and the program to be tested in parallel. Differences in their outputs are highlighted. File comparator. Compares the result of the program test with previous test results and reports differences between them. Comparators are particularly useful in regression testing, where the results of executing old and new versions are compared. Differences in these results indicate potential problems with the new version of the system. Report generator. Provides report definition and generation facilities for test results. Dynamic analyzer. Adds code to a program to count the number of times each statement has been executed after the tests have been run. An execution profile is generated showing how often each program statement has been executed. Test cases should be designed so that all the statements in the program are executed at least once. Simulator. Different kinds of simulator may be provided. Target simulators simulate the machine on which the program is to execute. User interface simulators are script-driven programs which simulate multiple simultaneous user interactions. Using simulators for I/O means that the timing of transaction sequence is repeatable. This is particularly useful when testing real-time systems which may contain subtle timing faults. The testing requirements for large systems depend on the application which is being developed. Consequently, testing workbenches invariably have to be adapted to suit the test plan of each system. Examples of adaptations which may be required are: scripts may have to be written for user interface simulators and patterns defined for test data generators. Report formats may also have to be defined. Sets of expected test results may have to be prepared manually if no previous program versions are available to serve as an oracle. Special purpose file comparators may have to be written which include knowledge of the structure of the test results on file. A significant amount of effort and time is usually needed to create a comprehensive testing workbench. In this case, the overall testing cost may be up to 50% of the total development cost, so testing workbench adaptation costs are usually justified.